A world with twin suns hangs in a sky above an ocean of liquid rock. This is not science fiction, but one of many real planets far beyond our solar system. We are embarking on a thrilling quest to count down the top 30 exoplanets that are the most promising candidates for hosting alien life. By the end of this journey, you will know which distant worlds are the best bets for finding our cosmic neighbors. We will explore planets bathed in eternal daylight and others that may be entirely covered in water. The mysteries are profound. Could a thin band of twilight on a locked world cradle living organisms? What kind of life could thrive under the glare of a red dwarf star? How many of these 30 worlds are truly waiting for us to find them? What do you think we will discover first? Our journey begins practically in our own backyard, a mere 4.2 light-years away. Orbiting the red dwarf star Proxima Centauri, the closest star to our Sun, is a rocky world named Proxima Centauri b. This planet sits snugly within its star's habitable zone, that special region where temperatures might be just right for liquid water to exist on the surface. But this world is a paradox of potential, because Proxima Centauri is a much cooler and smaller star than our Sun. Its habitable zone is incredibly close. Proxima b completes an entire orbit in just 11 days, and it is likely tidally locked. One side of the planet endures perpetual, scorching daylight, while the other is frozen in eternal, dark night. Life, if it exists here, might huddle in the thin, temperate band of twilight that separates these two extreme hemispheres. The planet also faces a formidable challenge from its parent star. Red dwarfs like Proxima Centauri are notorious for their violent outbursts, unleashing massive stellar flares and radiation that could strip away a planet's atmosphere over time. Yet, despite these harsh conditions, hope persists. Scientists speculate that a thick atmosphere or a global magnetic field could shield the surface, potentially creating pockets of stability. Imagine vast, alien ecosystems thriving under a dim, crimson sun, in oceans that never see the dark of space or the heat of noon. Proxima Centauri b presents a compelling and complex first entry on our list, a world that is both tantalizingly close and profoundly alien. From the closest star, we now travel to a system that rewrote the rules of planetary architecture. Orbiting the faint, ultra-cool dwarf star TRAPPIST-1, a mere 40 light-years away, is a world known as TRAPPIST-1e. This planet is not just another dot of light. It is one of 7 known Earth-sized worlds, all circling their star in a delicate, tightly packed dance. The entire system would fit comfortably within the orbit of Mercury around our Sun, creating a cosmic neighborhood of staggering density. TRAPPIST-1e stands out as the crown jewel of this system, a rocky world positioned perfectly within the star's habitable zone. Like Proxima b, it is likely tidally locked, with one face forever bathed in dim, reddish light and the other in endless darkness. But here, the potential for life along that thin twilight band, the Terminator line, feels even more profound. Imagine a landscape where the star itself appears 3 times larger in the sky than our Sun, a vast, dark crimson orb hanging motionless above the horizon. This system offers an unprecedented opportunity for science. With 7 Earth-sized planets so close to one another, studying their atmospheres becomes a realistic goal for the next generation of telescopes. We could soon analyze the air of TRAPPIST-1e, searching for the chemical fingerprints of water vapor, methane, or even oxygen. The discovery of such gases would not just hint at habitability. It could be our first strong signal of a living world. This system is a gift to astronomers, a complete laboratory for understanding how planets form and, just maybe, how life begins. The search for another Earth took a giant leap with the Kepler Space Telescope, an instrument that stared at a single patch of sky for years and revealed thousands of new worlds. Among its most profound discoveries are two planets that forever changed our perspective, our first true glimpses of distant cousins. The first of these, Kepler 186f, holds the historic title of being the very first Earth-sized planet we ever confirmed to be orbiting within the habitable zone of another star. Located about 500 light-years away, it circles a red dwarf star, much cooler than our Sun. While it is only slightly larger than our own world, its year is a mere 130 days long. The light that bathes its surface would feel dim and red to our eyes, a perpetual twilight glow. Yet, its discovery was a monumental proof of concept. It told us clearly that planets like ours, nestled in that just right zone, are not rare. They are out there. Its cousin, Kepler 452b, presents an even more hauntingly familiar picture. This world orbits a star that is a near twin to our own Sun, a star that is actually 1.5 billion years older. This has led scientists to wonder if Kepler 452b is not just a cousin, but a vision of Earth's own distant future. Imagine a planet with a similar size and orbit, but one that has experienced an extra 1.5 billion years of cosmic history. Its star has grown brighter with age, potentially causing a runaway greenhouse effect on the planet below. Is it a lush, mature world where life has had an immense head start? Or is it a scorched and barren desert, showing us a potential fate for our own world? We simply do not know yet, but together, these two Kepler discoveries represent critical steps in our quest. One proved that Earth-sized worlds in the habitable zone are common, while the other showed us that planets can exist around stars almost identical to our own for billions of years. They are not just dots of light. They are powerful symbols, telling us that the ingredients for life are scattered generously across the galaxy. Our journey now leads us to a trio of nearby super-Earths, each a tantalizing world in its own right. Just 40 light-years away, the planet LHS 1140b stands out for its incredible density. This world is a super-Earth, meaning it is larger than our own planet, but its composition is what truly sparks the imagination. LHS 1140b is so dense that astronomers are confident it is a rocky world, not a gaseous mini-Neptune. Some leading theories suggest its surface might be a global magma ocean, a vast, churning sea of molten rock simmering under a dim red sun. Yet, other models propose a far more intriguing possibility. This planet could be what scientists call a water world, an entire globe shrouded by an ocean hundreds of miles deep. The sheer pressure at the bottom of such an ocean would create exotic forms of ice, not cold, but hot and solid as rock. Could life persist in the lighter, liquid waters near the surface, in a perpetual star-lit sea? Not far off in cosmic terms, another promising candidate orbits the quiet star Gliese 357. The planet Gliese 357d sits squarely within its star's habitable zone. What makes this world particularly compelling is the nature of its sun. Unlike the volatile Proxima Centauri, Gliese 357 is a remarkably calm and quiet red dwarf. This tranquility is a boon for potential life, as it means the planet is likely spared from the relentless barrage of sterilizing radiation and atmosphere-stripping flares that plague other worlds. Under this steady, gentle starlight, Gliese 357d has a far better chance of holding onto a thick, protective atmosphere. Picture a landscape where the possibility of stable liquid water on the surface is not just a dream, but a real, enduring condition. This stability makes it one of the most promising targets for future study, a world where the ingredients for life could have been mixing for billions of years in relative peace. Then there is Tigardin Star B, a planet with one of the highest Earth Similarity Index scores ever measured. This index is a scientific tool that compares a planet's properties to our own world, and Tigardin B scores remarkably well. It is a rocky super-Earth orbiting a faint red dwarf just 12 light-years away, making it one of our closest planetary neighbors. Its orbit places it firmly in the star's habitable zone, and scientists calculate that its average surface temperature could be remarkably temperate, potentially even similar to Earth's. The conditions seem almost perfect on paper, but this world is also likely tidally locked, presenting that now familiar puzzle of a day side and a night side. Could its atmosphere redistribute heat effectively enough to make the entire planet livable? Or would life be confined to that narrow, eternal sunset strip? These three super-Earths, each with their own unique story of rock, water, and quiet starlight, expand our list with profound possibilities, reminding us that promising worlds are not just out there, they are practically next door. A new class of world has emerged from the data, planets that may not have any land at all. K218b stands as a landmark discovery, a super-Earth located 120 light-years away where astronomers made a historic detection. For the first time, they confirmed the presence of significant water vapor in the atmosphere of a planet within its star's habitable zone. This is not just a hint. It is a strong signal. This finding fuels the extraordinary hypothesis that K218b could be a Hycean world. Imagine a planet entirely enveloped by a global, deep ocean, with a thick, hydrogen-rich atmosphere creating a vast, warm, and water-drenched environment. In the eternal darkness of such an ocean's abyss, where pressures are immense, could life not only exist but thrive, completely independent of sunlight? It is a realm where our very definitions of habitability are rewritten. Not long after, the TESS mission added another crucial piece to the puzzle with the discovery of TOI 700d. This world is a stark contrast to the large super-Earths. It is an Earth-sized planet, almost exactly the same dimensions as our own, orbiting a quiet red dwarf star 100 light-years away. Its orbit is perfectly situated within the star's habitable zone, and its parent star shows no signs of the violent flares that threaten other systems. This combination of factors makes TOI 700d one of the most compelling Earth-like candidates we have ever found. Think of a world with a similar surface gravity to our own, bathed in gentle, steady starlight, with every chance of hosting liquid water. Is its surface a global ocean, or does it have continents we cannot yet see? These two planets, one a vast Hycean world and the other a potential Earth twin, represent two very different, yet equally promising, pathways for life. One suggests that life could flourish in environments we once thought impossible, while the other hints that worlds strikingly similar to our own are waiting to be found. These three super-Earths challenge our very definition of a solar system. Orbiting the red dwarf JJ667c, the planet JJ667cc exists within a triple star system. This means its sky could be illuminated by not one, but three suns, a breathtaking sight of multiple orbs casting complex, shifting shadows. The planet itself is a massive super-Earth, over 3.5 times heavier than our own world. This substantial mass gives it a strong gravitational pull, which could be the key to its survival. A thick, dense atmosphere might cling to this world, protecting it from the variable influences of its stellar trio and potentially creating a stable, warm environment capable of hosting vast oceans. The cosmic ballet of three stars raises fascinating questions. Could such a complex gravitational environment stir a planet's interior, fueling volcanic activity that replenishes a life-giving atmosphere? Next, we find a world in a far more solitary orbit. HD 40307G is a super-Earth circling a star much like our own Sun. Its path is special, taking it along the outer, cooler edge of its star's habitable zone. This position is a delicate balance. It receives just enough stellar warmth to potentially allow for liquid water, but not so much that it would boil away into space. This world might be a cold, rocky planet, a place where life would need to cling to geothermal heat sources near volcanoes or deep in the crust. Alternatively, if it possesses a thick atmosphere rich in greenhouse gases like carbon dioxide, it could effectively trap enough heat to become a temperate, Earth-like paradise. This planet embodies the Goldilocks principle, showing us that the habitable zone is not a single line, but a broad spectrum of possibilities. Then there is Tau Ceti e, a world that has sparked intense debate among astronomers. It orbits a star, Tau Ceti, that is a virtual twin of our Sun in both size and brightness, located a mere 12 light-years away. This Sun-like star makes the system feel hauntingly familiar. Tau Ceti e, however, is a super-Earth that orbits very close to its star, completing a year in just 168 days. This places it on the hot, inner edge of the habitable zone. Some models suggest this world could be a scorching Venus-like hellscape, with surface temperatures soaring high enough to melt lead, its atmosphere thick with crushing carbon dioxide. Yet, other simulations leave the door open for a more surprising reality. If Tau Ceti e has the right atmospheric composition, perhaps one with reflective clouds or a lower proportion of greenhouse gases, it could still maintain temperate conditions. The possibility that a world so close to a Sun-like star could be habitable is a profound one. It suggests that solar systems like our own might commonly host planets where life could take root, not just on the outer edges, but closer in as well. These three worlds, one dancing with multiple suns, one balancing on the cool frontier, and one simmering near a familiar star, show us that the architecture of life is far more flexible and wondrous than we ever imagined. Just 12 light-years away, Wolf 1061c feels almost like a neighbor in our galactic community. This super-Earth sits squarely within what astronomers call the conservative habitable zone of its red dwarf star, a more restrictive definition that focuses on the most Earth-like conditions possible. Its orbit is stable and calm, suggesting a world with a predictable climate, at least by the tumultuous standards of red dwarf systems. Yet, this proximity to its star almost certainly means it is tidally locked. The eternal day side could be scorching, while the night side is frozen solid, leaving that narrow twilight band as the prime real estate for any potential life. The planet's mass is over 4 times that of Earth, which could mean a stronger surface gravity and the potential for a very thick atmosphere to distribute heat around the globe. Could powerful winds constantly scour the Terminator line, making it a turbulent place to exist? Gliese 832c, only 16 light-years distant, presents a similar puzzle with a different twist. It boasts one of the highest Earth Similarity Index scores we have calculated, meaning its size, density, and the energy it receives from its star are remarkably close to our own worlds. On paper, it looks like one of our best candidates for an Earth twin, But the reality is likely far stranger. This super-Earth is also tidally locked to its star. The challenges here are immense. Without a rotating day and night cycle, the atmosphere itself might struggle to function. One side could be perpetually boiling away any water, while the other side condenses it into a planet-spanning ice cap. For life to persist, it would need a truly robust atmosphere to circulate heat and moisture, or it would have to find refuge deep underground, powered by the planet's internal warmth rather than the dim light of its sun. These two nearby worlds remind us that a high potential for life does not always mean a familiar environment. They are so close we can almost touch them with our telescopes, yet they remain enigmatic, their surfaces a mystery of extreme contrasts where life would have to be as hardy as it is alien. Far beyond our own solar system, the Kepler telescope unveiled a pair of orbiting worlds that have captivated scientists for years. Kepler 62e and Kepler 62f are two super-Earths circling the same star, a star cooler and older than our Sun. Kepler 62e is the inner of the pair, a world about 60% larger than Earth. Its position on the warm, inner edge of the habitable zone has led to a compelling theory. Many astronomers believe this planet could be a true water world, a globe completely shrouded by a deep, global ocean with no land in sight. Imagine an endless expanse of water under a dim orange sun, with pressures at the bottom creating exotic forms of ice. Life here would be entirely aquatic, potentially thriving in a world ocean of immense scale. Its sibling, Kepler 62f, is the smaller and cooler of the two. It is only about 40% larger than Earth, making it one of the most Earth-sized planets ever found in a habitable zone at the time of its discovery. It orbits farther out, receiving a gentler glow from its star. This distance suggests it could be a colder world, perhaps one locked in a global ice age. Yet, if it possesses a thick atmosphere rich in greenhouse gases, it could trap enough heat to host liquid water and vast, frigid seas along its equator. These two planets present a fascinating duality, two very different potential environments for life in the same stellar family. Then there is Kepler 442b, a world that stands apart for one remarkable reason. It has received one of the highest ratings for its potential to host not just life, but a very specific kind. Scientists calculate that this super-Earth receives just enough of the right kind of light from its orange dwarf star to theoretically support photosynthesis. This is a staggering thought. The surface of Kepler 442b could be bathed in starlight with a similar energy profile to Earth's, potentially allowing plant-like organisms to convert light into chemical energy. Picture an alien landscape not in perpetual red twilight, but under a sun that might feel strangely familiar to earthly plants. Could its continents, if it has any, be covered in vast forests of alien vegetation, their leaves adapted to the specific spectrum of their sun? Of all the worlds we have encountered, Kepler 442b offers one of the most direct visions of a truly living world, a planet where the fundamental process that powers most life on Earth might also be at work under an alien sky. Some planets ignite not just curiosity, but fierce debate. Orbiting the orange dwarf star HD 85512, the super-Earth known as HD 85512b presents a fascinating puzzle where habitability hinges on a single, delicate factor. This world sits on the warm, inner edge of its star's habitable zone. Without any atmosphere, its surface would be far too hot for liquid water. But scientists have run the models, and the results are startling. If this planet has just 50% cloud cover, Those reflective white clouds could bounce enough stellar heat back into space to create a perfectly temperate climate. Picture a world where the sky is perpetually dappled with clouds, a global shield that maintains just the right conditions for vast oceans to lap against alien shores. It is a reminder that a planet's climate is not just about its orbit, but the intricate interplay of its air and skies. The controversy deepens with a world that might not even exist, or might be one of our greatest finds. Gliese 581g was proposed as a super-Earth orbiting within the habitable zone of its quiet red dwarf star. Its discovery, however, was mired in statistical uncertainty. Some research teams insist the signal is just noise in the data, a ghost planet conjured by the complex wobbles of its star. Others stand firmly by their analysis, arguing that Gliese 581g is not only real, but a prime candidate for liquid water. If it is there, its mass suggests it could hold onto a thick atmosphere, and its position is ideal for stable, Earth-like temperatures. The scientific battle over this world's very existence highlights the incredible challenge of finding planets so far away. We are left with a profound question. Is Gliese 581g a mirage, or is it a hidden oasis, one of the most promising water worlds waiting just 20 light-years from Earth? The debate itself proves how high the stakes are in our search for a living world. The search for a true Earth twin often feels like chasing a ghost, but Kepler 1649c comes remarkably close. Discovered by scientists reanalyzing old Kepler data, this world is a revelation. It is almost exactly the same size as our own planet, and it receives about 75% of the starlight that Earth gets from the Sun. This combination of a familiar scale and a familiar amount of energy makes it one of the most Earth-like worlds we have ever found, orbiting comfortably within its red dwarf's habitable zone. Yet its years are incredibly short, just 19.5 days, and it is almost certainly tidally locked. Life here would exist under a dim, fixed sun, but the potential for liquid water seems strong. It is a powerful reminder that hidden gems can be found in our own data, a near-Earth twin waiting in the archives. From this promising world, we return to our closest stellar neighbor, but to a very different kind of planet. Proxima Centauri c is the second world discovered orbiting Proxima Centauri, and it could not be more different from its inner sibling. This planet is a super-Earth, orbiting far beyond the habitable zone in a region of deep cold. Its year lasts over 5 Earth years, and its surface is likely a frozen wasteland. The intense intrigue around Proxima Centauri c lies in its nature. Is it a rocky super-Earth, a small gas planet, or even a massive, solid world encased in a thick shell of ice? Some theories even suggest it could be a captured rogue planet, a world that formed in the depths of interstellar space and was later snared by the star's gravity. This frigid outlier in the Proxima Centauri system proves that even a single star can host a menagerie of wildly different worlds. Then we have Ross 128b, a world that offers something precious: stability. Orbiting a quiet, inactive red dwarf star just 11 light-years away, this super-Earth presents one of the most serene environments we have yet identified. Unlike the flare-prone Proxima Centauri, its parent star is calm and gentle, offering a steady, unwavering light. This tranquility is a game-changer for potential life. It means Ross 128b has likely been spared the atmospheric destruction that ravages other worlds, giving it billions of years of uninterrupted peace to develop and evolve. Its position in the habitable zone is perfect, and its quiet sun makes it a primary target for the next generation of telescopes. When we finally train our most powerful instruments on this world, we may be able to peer directly into its atmosphere, searching for the telltale signs of biological activity without the interference of stellar tantrums. These three worlds, a near-Earth twin, a frozen enigma, and a serene oasis, show us that the search for life is not a single path, but a branching exploration of countless possibilities. Long before we knew of Hycean worlds or Earth's near twins, two early discoveries expanded our very idea of what a habitable planet could be. The first of these, Kepler-22b, holds a special place in history. It was the very first planet ever confirmed by the Kepler telescope to be orbiting squarely within the habitable zone of a sun-like star. The announcement sent ripples of excitement around the world. Here was a world about twice the size of Earth, receiving a gentle glow from its star that suggested a balmy average surface temperature of around 72 degrees Fahrenheit. It sounded for a moment like a perfect paradise, but further study revealed a more complex and intriguing reality. Kepler-22b is now thought to be a mini-Neptune, a type of planet unlike any in our own solar system. This means it likely has a small, rocky core, but that core is utterly engulfed by a vast, deep, and opaque atmosphere of hydrogen and helium. There is probably no solid surface to stand on. Instead, any potential life would have to be airborne, floating high in the skies within temperate cloud layers, forever adrift in a gaseous sea. Its discovery taught us that the habitable zone is not just for rocky planets, but for enigmatic worlds that challenge our Earth-centric views. Around the same time, another discovery presented a different kind of mystery. GJ-1214b is a super-Earth orbiting so close to its red dwarf star that its year lasts just 38 hours. When astronomers pointed the Hubble Space Telescope at this world, they witnessed something strange. As the planet passed in front of its star, the starlight filtered through its atmosphere revealed nothing at all. The atmosphere was featureless, showing no chemical fingerprints of the molecules they were searching for. This blank slate could mean one of two extraordinary things. The first possibility is that JJ-1214b is a water world, shrouded by a thick, steamy atmosphere rich in water vapor that creates a uniform, opaque blanket. The second is that it is a gaseous planet with a high-altitude layer of thick photochemical haze, a global smog that obscures our view of the layers below. Both scenarios are compelling. One points to a global ocean under a crushing, hot steam atmosphere, while the other suggests a complex atmospheric chemistry we are only beginning to understand. Together, Kepler-22b and JJ-1214b laid the groundwork for modern exoplanet science. One showed us that habitable conditions might exist in the skies of gas-shrouded worlds, while the other presented us with a stark, featureless mystery, a reminder that some of the universe's most profound secrets are still hidden behind a veil. The promise of habitable worlds is shadowed by the sheer diversity of planets that exist, including those of unimaginable extremes. Take HD2-19134b, a scorching super-Earth located a mere 21 light-years away. This world is one of the closest rocky planets we have ever found outside our solar system. It whips around its star in just 3 days, and its surface temperature is hot enough to melt metal. Yet, its existence is critically important. By confirming it is a terrestrial world with a solid surface, it proves that super-Earths can be made of rock and metal, just like our own planet, even if their environments are utterly hellish. It is a foundational discovery, a nearby laboratory showing us the basic building blocks of planets are common. Then there is 55 Cancri E, a world that defies even the wildest imagination. This super-Earth orbits so close to its sun-like star that a single year passes in only 18 hours. The daytime temperature soars to over 4,000 degrees Fahrenheit. At such infernal heat, the very rocks on the surface would not simply melt. They would boil, creating global oceans of molten lava. But the strangeness does not end there. Astronomers studying the planet's density and composition believe it is rich in carbon. This has led to a stunning theory. Much of the planet's interior could be composed of diamond, a glittering core of crystallized carbon forged in the star's intense heat. Picture a world with a surface of simmering lava under a black, star-filled sky, all floating atop a fortune of diamond larger than our entire planet. These worlds show us that the cosmos harbors not just potential gardens, but also forges of incredible violence and wealth. In stark contrast, the gas giant WASP 96b offered a crystal-clear view into planetary science. When this planet passed in front of its star, telescopes detected a pristine, cloud-free atmosphere. For the first time, scientists could see deep into the air of a distant world without the obscuring veil of clouds or haze. The spectrum of starlight filtering through its atmosphere revealed the unambiguous fingerprint of sodium, like a perfectly clean window into its gaseous composition. This breakthrough proves we can directly analyze the chemical makeup of exoplanet atmospheres, a vital skill we will need to search for signs of life on more temperate worlds in the future. These three planets, a confirmed rocky inferno, a hypothetical diamond world, and a cloudless gas giant, demonstrate the full spectrum of planetary science. They are the extreme laboratories where we learn to read the stories written in alien air and rock. Our final trio of worlds brings us to the very edge of habitability, where hope is tempered by harsh reality. Kepler 438b was once a shining star on our list, an Earth-sized planet orbiting within the habitable zone of its red dwarf star. For a time, it was considered one of the most promising candidates, a world that seemed to tick all the boxes for potential life. But then astronomers looked more closely at its sun. They discovered that Kepler 438 is a violently active star, prone to erupting in superflares of immense power. These stellar explosions are so intense they are thought to have stripped away the planet's atmosphere long ago, leaving behind a barren, irradiated rock. This world serves as a crucial lesson. A perfect orbit means nothing if the local star is a hostile neighbor, turning a potential paradise into a lifeless husk. Its story is a poignant reminder of how fragile the conditions for life can be. The next world, Kepler 443b, presents a different kind of limitation. This super-Earth does indeed orbit within its star's habitable zone, but its chances for life are considered remarkably low. Why? Because it resides on the very outer fringe of that zone, receiving only a faint trickle of warmth from its star. Scientists have calculated that there is less than a 2% probability that this world is rocky and could support liquid water on its surface. It is far more likely a small, gaseous mini-Neptune, a type of planet with no solid surface, where any water would be trapped as vapor deep within a crushing atmosphere. Kepler 443b shows us that simply being in the right region is not enough. The planet's own fundamental nature ultimately dictates its fate. And then we come to our 30th and final world, a place that redefines the word extreme. Kelt 9b is one of the hottest planets ever discovered. It is a gas giant orbiting so close to its blue giant star that its year is less than 2 Earth days. The stellar radiation bombarding the planet is so intense that its dayside temperature soars to over 7,800 degrees Fahrenheit, hotter than the surface of some stars. This is not merely a hot world. It is a world being actively destroyed. The incredible heat is literally boiling its atmosphere away, creating a vast, glowing tail of evaporated gas that streams behind the planet like a comet. Kelt 9b is a temporary spectacle, a planet in its death throes, being slowly vaporized by its own sun. These three worlds, one sterilized by its star, one likely incapable of supporting life, and one being torn apart, complete our list of 30. They are not stories of failure, but of context. They show us the full spectrum of planetary existence, from the serene to the cataclysmic, framing our entire search for life within the incredible and often unforgiving diversity of the cosmos. This narrow band of possibility is defined by a single, remarkable molecule, liquid water. Why does life as we know it depend so completely on this one substance? Water is a universal solvent, capable of dissolving a vast array of chemicals and allowing them to mingle and react in ways that solid rock or gas alone cannot. It acts as a medium for transporting nutrients and waste within living cells. Its very structure helps fold proteins and form the membranes that are the foundation of biology. A planet with persistent liquid water on its surface is a planet that has passed the first and most crucial test for life. This is why astronomers call it the habitable zone, or more poetically, the Goldilocks zone. It is not too hot, where water would boil away into vapor, and not too cold, where it would freeze into permanent ice. It has to be just right, but the location of this perfect zone is not fixed. It shifts dramatically depending on the star at the center of a solar system. Around a massive, brilliant blue giant, the habitable zone would be pushed far out in the system, a distant and lonely orbit. For a small, dim red dwarf, the zone is incredibly close, so tight that planets within it are often gravitationally locked, with one face in permanent light and the other in endless dark. Our own sun, a middle-aged yellow dwarf star, offers a comfortably spaced habitable zone where Earth resides. Yet a planet's orbit is only the beginning of the story. A world can be perfectly placed and still be a barren wasteland, or exist on the fringe and potentially teem with life. The true regulator of a planet's climate is its atmosphere. Venus, for instance, lies at the inner edge of our sun's habitable zone, but a runaway greenhouse effect has turned it into a scorching hellscape. Mars, on the outer edge, has a thin atmosphere that cannot retain enough heat, leaving it a frozen desert. A thick atmosphere rich in certain gases can act as a blanket, trapping heat and warming a planet that would otherwise be too cold. This is why a super-Earth like J667cc, far from its star, could still host liquid water if it has an atmosphere with sufficient greenhouse gases. Conversely, a planet that seems too hot might be saved by reflective cloud cover, bouncing stellar radiation back into space. Geology plays a role too. A planet with active volcanoes can constantly replenish its atmosphere, releasing gases that warm the planet and cycle essential elements. A strong magnetic field, generated by a molten core, can deflect the sterilizing radiation from its star, protecting any nascent life on the surface. So the habitable zone is not a simple bullseye. It is a dynamic concept, a starting point that must be refined by the complex and wonderful interplay of a world's air, its rocks, and its own internal fire. Red dwarfs present the greatest paradox in our search for life. These faint, cool stars make up over 70% of all stars in our galaxy, meaning the vast majority of potential homes for life orbit them. Worlds like Proxima Centauri b and TRAPPIST-1e are not cosmic oddities. They are the standard model for a habitable planet. Their stars offer one monumental advantage: stability. A red dwarf can burn for trillions of years, far longer than the total expected lifespan of the universe. This provides an almost unimaginable amount of time for life to arise, evolve, and complexify on any suitable worlds in their care. Imagine a civilization that has had not just millions, but billions of extra years to develop under a constant crimson sun. Yet, this promise of longevity comes with severe and immediate challenges. The very proximity that places a planet in the habitable zone also locks it gravitationally. Tidal locking means one hemisphere is a permanent furnace, while the other is a deep freeze. For a world like TRAPPIST-1e, the only temperate region might be a narrow, eternal dusk zone, a razor's edge between fire and ice where winds of unimaginable force could howl ceaselessly. But perhaps the most dire threat comes from the stars themselves, especially in their youth. Young red dwarfs are notoriously violent, frequently erupting in colossal stellar flares that can double their brightness in mere minutes. These eruptions blast out ultraviolet and X-ray radiation, which can scour a planet's atmosphere, stripping it away molecule by molecule over millions of years. A world like Proxima b is subjected to these blasts regularly, leaving us to wonder if any protective atmosphere could possibly remain. This is the red dwarf conundrum in a nutshell. Does the incredible stability and longevity of these stars ultimately provide a safe harbor for life to flourish over eons? Or do the brutal realities of tidal locking and stellar fury render their planets barren, irradiated rocks? The answer may lie not in the stars, but in the planets themselves. A strong magnetic field could deflect the worst of the radiation. A thick, primordial atmosphere might resist being stripped away. Or perhaps life on such worlds would not exist on the surface at all, but deep underground, sheltered from the tantrums of its dim sun. The prevalence of these systems tells us one thing for certain. If life is common in our galaxy, it is far more likely to be found under a red sun than a yellow one. A super-Earth is not necessarily a larger version of our own world. It is a classification based purely on mass, a title given to any planet heavier than Earth but lighter than Neptune. This simple definition, however, masks a profound cosmic divide. The most common type of planet we have found in the galaxy sits squarely in this ambiguous middle ground, forcing us to ask a critical question. Is a given super-Earth a scaled-up, rocky world with continents, mountains, and a potential for life? Or is it something entirely different, a gaseous mini-Neptune with no solid surface at all? The distinction is everything, for it separates a potential habitat from a gaseous abyss. To solve this puzzle, scientists perform a kind of cosmic weigh-in. They need two key measurements: the planet's radius and its mass. The radius is often measured as the planet passes in front of its star, causing a tiny, predictable dip in the star's light. The mass is trickier, usually determined by the subtle wobble the planet's gravity induces in its parent star. With both the size and the weight of a planet in hand, astronomers can calculate its density. Think of it as the difference between a cannonball and a balloon. They might be the same size, but their weights are vastly different because one is solid iron and the other is mostly empty space. A planet with a high density like Earth must be made of rock and metal. A planet with a low density like Saturn is a puffy ball of hydrogen and helium gas. A super-Earth with a density similar to Earth's is almost certainly a terrestrial world, a massive rocky planet. It could have towering mountains and deep canyons, and if it lies within the habitable zone, it might even have vast oceans lapping against its shores. But if its density is low, it is a mini-Neptune. Such a world would have a small, rocky core utterly engulfed by a deep, thick atmosphere thousands of miles deep. There is no ocean surface to sail on, no continent to stand upon. The pressure and temperature would increase dramatically as you descend, eventually crushing any probe into scrap metal. For life as we know it, this is a critical barrier. While we can imagine bizarre, floating life forms in the upper cloud decks of a gas giant, a solid surface with liquid water is a far more reliable recipe for the chemistry of life. This is why the hunt is not just for planets in the habitable zone, but for dense, rocky planets within it. Every time we measure the mass and radius of a promising super-Earth, we are asking the universe a direct question. Are you a world or are you a cloud? The answer determines whether we are looking at a new Earth or a permanent mystery. An atmosphere is more than just a layer of air. It is a planet's shield, its climate control system, and the very canvas upon which life can paint its story. Without this vital blanket, a world is exposed to the harsh vacuum of space, its surface temperatures swinging violently between scorching days and freezing nights. Our own moon demonstrates this stark reality, where a single day can see temperatures soar to 260 degrees Fahrenheit and then plummet to 280 degrees below zero. An atmosphere prevents these extremes, acting as a global insulator that smooths out the temperature across the planet. It creates the necessary pressure to keep water in its liquid state, preventing it from instantly boiling away into vapor or freezing solid. Perhaps most importantly, a thick atmosphere is our first line of defense against the constant barrage of high-energy radiation and deadly ultraviolet light from a star. It serves as a protective barrier, absorbing or deflecting these harmful particles long before they can reach the surface and damage fragile organic molecules. But how can we possibly know what the air is like on a world trillions of miles away? The answer lies in a technique as elegant as it is powerful, a method called transmission spectroscopy. When a distant exoplanet passes directly in front of its star from our viewpoint, a tiny fraction of the star's light filters through the planet's thin outer atmosphere. Different gases in that atmosphere absorb specific, unique colors or wavelengths of that starlight. It is as if each molecule leaves its own distinct fingerprint on the light that passes through. By carefully analyzing the spectrum of the star's light both before and during this transit, scientists can detect which colors are missing. Those minuscule, telltale dips in the spectrum reveal the chemical composition of the alien air. We can identify the presence of water vapor, methane, carbon dioxide, and even oxygen. This is how we knew that K218b had water vapor in its atmosphere, and how we found the cloudless skies of WASP 96b. We are, in effect, reading the story of these distant worlds written in rainbows of filtered starlight, searching for the atmospheric signatures that might just point to a world that is not only habitable, but already inhabited. The universe's harshest environments often hide its most resilient secrets, right here on our own planet, in the scalding, acidic waters of Yellowstone's hot springs, where the pH is low enough to dissolve metal. Entire colonies of microorganisms called thermoacidophiles not only survive, they thrive. At the bottom of the ocean, under crushing pressures and in total darkness, hydrothermal vents spew superheated, mineral-rich water that would be instantly lethal to most life. Yet these volcanic chimneys are surrounded by bizarre ecosystems of tube worms and giant clams, all sustained by chemosynthesis, a process that uses chemical energy instead of sunlight. Life in these places does not merely endure extreme conditions, it requires them. These organisms, known as extremophiles, are not fringe curiosities. They are a fundamental rewriting of the rules for life. If life can flourish in a boiling acid bath or in the frigid, radiation-drenched sands of the Atacama Desert, then our entire concept of a habitable world must dramatically expand. Suddenly, a planet like JJ 1214b, shrouded in a thick, steamy atmosphere, is not a doomed pressure cooker, but a potential global hot spring. A frozen super-Earth on the outer edge of its habitable zone is not a dead ice ball, but a world that might harbor life deep beneath its frozen crust, warmed by planetary heat. The existence of extremophiles forces us to look past the comfortable, Earth-like conditions we instinctively seek. It asks us to consider that the most common forms of life in the cosmos might not be green fields under a yellow sun, but strange, hardy organisms thriving in the eternal night of a global ocean or deep within the rocks of a tidally locked world. Our search is no longer just for a second Earth, but for any world where the relentless, creative force of life has found a foothold, no matter how alien the environment may seem. This stark division between day and night is a direct consequence of a planet being tidally locked. The same gravitational forces that cause our moon to always show one face to Earth can, over millions of years, slow a planet's rotation until it perfectly matches its orbital period. The result is a world permanently fixed in place, with one hemisphere eternally basking in the light of its star, and the other plunged into an endless, frozen darkness. For a long time, such a world was written off as a hopeless case, a place where the day side would bake any oceans into vapor, and the night side would freeze its atmosphere solid. But nature is far more inventive than our first assumptions. The key to survival on these worlds may lie in that very line of separation, the terminator zone. This is the narrow, ribbon-like border where perpetual sunrise meets eternal sunset. Here, temperatures could be stable and moderate, a direct result of the constant, gentle mixing of air. On the scorching day side, the heated atmosphere would rise, creating a powerful flow of wind that rushes toward the cold, dense air of the night side. This relentless atmospheric river would constantly funnel warmth toward the dark hemisphere and pull cooler air back toward the light, creating a global weather system centered entirely on this twilight band. What would it be like to stand on such a world? The star would hang motionless and immense, forever fixed on the horizon. You would be standing in an eternal dawn, or perhaps an eternal dusk, with the landscape stretching away into a searing brightness on one side and an abyssal blackness on the other. Powerful winds might be a constant feature of this environment, but within that turbulence, pockets of stunning stability could exist. Life here would not experience days or seasons as we know them. Any photosynthetic organisms would have to adapt to a sun that never moves, their leaves permanently angled toward the low red light. The very concept of migration would be redefined, with creatures perhaps moving in elevation rather than latitude to find their perfect temperature. This terminator line is not a barren no man's land, but a potential oasis, a world within a world, proving that life can find a way in the most constrained and unforgiving of circumstances. This search for atmospheric whispers finds its ultimate instrument in the James Webb Space Telescope. Orbiting 1,000,000 miles from Earth, its golden mirror is not designed to capture pretty pictures of planets, but to read their secrets in the language of infrared light. This is the key to its revolutionary power. When a planet passes in front of its star, the star's light filters through the planet's thin outer atmosphere. Different gases in that air absorb specific, unique colors of this light. For Earth-like planets orbiting cooler stars, this light is brightest in the infrared part of the spectrum, exactly where Webb's instruments are exquisitely tuned to see. It can detect the faintest chemical fingerprints left in the starlight, transforming a distant point of light into a world with a story we can read. The telescope's primary mission is to analyze these atmospheric spectra, searching for the subtle combinations of gases that could betray the presence of life. The most tantalizing of these are biosignatures. A large amount of oxygen, for instance, is a powerful signal. In an atmosphere, oxygen is highly reactive and quickly bonds with rocks and other elements. For it to build up to significant levels, something must be constantly replenishing it, a process like photosynthesis used by plants on Earth. Finding oxygen and methane together would be an even stronger clue, as these gases react with each other and would vanish quickly unless a continuous source, perhaps a living biosphere, was producing them. But Webb's vision is so sharp it could potentially detect technosignatures, gases that have no natural explanation. Imagine detecting chlorofluorocarbons, or CFCs, in the air of a world light years away. These complex industrial pollutants would point unequivocally to an advanced civilization capable of altering its own planet. The James Webb Space Telescope is our generation's greatest tool in this cosmic quest. It is not just looking for planets in the habitable zone. It is listening to their air, waiting for the moment a distant atmosphere speaks, and tells us we are not alone. The ultimate goal is not just to find a planet's chemical signature, but to see the world itself. We are on the cusp of a new era of exploration, one where our tools will evolve from detecting wobbles in starlight to capturing the pale blue dot of a distant Earth. The next generation of observatories, both in space and on the ground, are being designed with this single, breathtaking ambition in mind. Imagine a space telescope so powerful it could directly image an exoplanet, separating its faint, shimmering light from the overwhelming glare of its parent star. This is the promise of the Habitable Worlds Observatory, a monumental mission concept now being planned by NASA. Its primary mission would be to survey dozens of the nearest Sun-like stars, seeking out Earth-sized planets within their habitable zones. But it would not stop at simply finding them. Using a sophisticated coronagraph, an instrument that acts like a high-tech hand blocking out the star's light, it would take a direct picture of these worlds. We would not see continents or oceans in detail, but we would see a point of light. By analyzing the spectrum of that single, precious pixel, we could determine the color of the planet. Does it look blue, hinting at vast oceans? Does it show the reddish hue of deserts, or the green tint that could, just maybe, indicate the presence of alien vegetation? This single pixel would contain a universe of information, telling us for the first time what an alien Earth truly looks like. On the ground, a parallel revolution is taking shape. In the high, dry deserts of Chile, the extremely large telescope, or ELT, is slowly rising from the mountain rock. Its primary mirror will be an astonishing 39 meters across, a colossal eye that will gather more light than all of the world's major optical research telescopes combined. This immense power will allow it to push the boundaries of direct imaging even further. The ELT might be able to study the rotation of some of the largest nearby exoplanets, watching for changes in their brightness and color that could map out continents and weather patterns over time. It could even analyze the atmospheres of planets around the closest stars with unprecedented precision, searching for the complex combinations of gases that scream of biological activity. These missions represent a fundamental shift. We are moving from an age of inference to an age of observation. Soon, we will not just be guessing about these worlds from the wobble of a star or the dip in its light. We will be looking at them, studying them as real places, and asking the most profound question of all. Is that faint, colored dot in the void a living world? Speculating on the appearance of alien life forces us to abandon our Earth-centric perspective. The creatures that might evolve on a super-Earth, with gravity twice as strong as our own, would not be tall and slender. Such forms would collapse under the immense weight. Life there would likely be stout and low to the ground, perhaps with multiple, powerful legs to distribute the strain, moving through a world where falling is far more dangerous. In the dense, hydrogen-rich atmosphere of a mini-Neptune, life would have no solid ground at all. Here, biology could take to the skies. We might find vast, balloon-like organisms, filled with gases lighter than air, drifting eternally through temperate cloud layers. They could filter nutrients from the air itself, growing to sizes that dwarf our blue whales, their forms shimmering with iridescent colors as they float through the perpetual twilight. The very chemistry of life might be different. On Earth, life is carbon-based, but in extreme environments, could silicon serve as the backbone for biology? Silicon can form complex molecules, much like carbon, but it does so more reluctantly. A silicon-based life form would likely exist in a world of much higher temperatures, perhaps on a planet so close to its star that the very rocks are molten at the surface. Such a creature might have a crystalline structure, its metabolism slow and geological, living and dying over millennia instead of years. And then there is the question of energy. We are children of the sun, our world powered by photosynthesis. But on a rogue planet, flung from its star and drifting in the cold of interstellar space, no sunlight ever reaches the surface. There, life would have to find another way. Around deep sea vents on Earth, entire ecosystems thrive on chemosynthesis, using the chemical energy from the planet's core. On a lonely rogue world, life could persist in subsurface oceans, warmed by radioactive decay in the rock, glowing in the absolute darkness with their own internal bioluminescent light. Alien life does not have to look like us, or anything we have ever seen. It could be a collective intelligence, a distributed network of fungal threads covering a continent, or a creature that perceives the world through magnetic fields rather than light. The universe's palette for life is unimaginably vast, limited only by the fundamental laws of physics and chemistry. With 30 promising worlds on our list, the silence from the cosmos feels louder than ever. This is the heart of the Fermi paradox, the haunting question that asks why, in a galaxy seemingly filled with potential, we have found no evidence of other civilizations. One chilling possibility is the Great Filter Hypothesis. This theory suggests that at some point in the evolution of life, from simple cells to interstellar explorers, there exists an almost insurmountable barrier. This filter could lie in our past. Perhaps the leap from non-living chemistry to the first self-replicating cell is so astronomically rare that it has only happened once. Or the filter could be ahead of us. It might be that all advanced civilizations inevitably discover a technology, perhaps related to artificial intelligence or weaponry, that leads to their own destruction. If this is true, then our own future may hold a test that no one has yet passed. A more optimistic, though equally strange, idea is the zoo hypothesis. This concept proposes that advanced civilizations are fully aware of our existence, but have chosen to place us in a kind of cosmic quarantine. They observe us from a distance, allowing humanity to develop naturally without interference, much like we observe animals in a protected wildlife reserve. Perhaps they are waiting for us to reach a specific technological or ethical milestone before making contact. Then there is the simplest, and in some ways most profound, explanation. Space is vast beyond human comprehension, and time is even deeper. The galaxy is over 100,000 light-years across, and civilizations may rise and fall over millions of years. What are the chances that another society is broadcasting signals at the exact same sliver of cosmic time that we are listening? We might be like ships passing in an endless, dark ocean, separated not just by immense distance, but by the eons that lie between our moments of existence. Our list of 30 worlds proves the ingredients for life are abundant. The silence that follows simply reminds us that finding a house does not mean someone is home, or that they are willing to answer the door. From the simmering magma oceans of LHS 1114b to the serene, steady starlight bathing Ross 128b, our journey across 30 worlds reveals a cosmos teeming with possibility. We have encountered planets cloaked in global oceans, worlds locked in eternal twilight, and systems where 7 siblings orbit a single dim star. Each one rewrites the rules of what a habitable world can be, proving that life, if it exists, will be as diverse and inventive as the universe itself. To find a single microbe thriving on any of these distant globes would be a discovery that echoes through all of human history. It would answer our oldest question, revealing that we are not a solitary fluke, but part of a vast, cosmic tapestry of life. That profound knowledge is now within our reach, waiting for the next generation of telescopes to turn their gaze upon these tantalizing targets. This search belongs to all of us. The next time you find yourself under a clear night sky, look up at those points of light. Remember that around them, entire worlds are turning, oceans are swirling, and the conditions for life are being tested in countless ways. Your curiosity is the fuel for this grand adventure. Keep looking up, keep wondering, and join us as we continue to explore the deepest mysteries of the cosmos.